Here we're going to talk about the technique of completing the square to solve quadratic equations. So in previous courses, and of course in the previous videos that you may have seen, we solve quadratic equations usually by just factoring. Now we're going to introduce this method of completing the square, which always works, and only because it is a cousin of the quadratic formula. In fact, we can use completing the square to derive the quadratic formula. So we'll have to recall this special factorization here, the special product here. If I want to expand this binomial here, x plus y squared, then this comes out as x squared plus 2xy plus y squared. And you can check that for yourself when you FOIL it out. And the goal of completing the square is to write a quadratic equation, something like this. And in fact, in general, I should write this as ax squared plus bx plus c, though you'll see that the method works when I transform my equation into a monic polynomial. That's one where the coefficient is 1. So I want to write this quadratic ax squared plus bx plus c as something squared plus something. And in something squared, I have x plus something, and that's going to be squared. The idea is I want to be able to express this as square so I can effectively use square roots to solve my quadratic equation. Now, this comes in two parts. The second part of completing the square is writing expressions in this form. We'll come back to this when we start talking about conic sections, in particular the parabola. This is actually most useful for writing parabolas in vertex form and other applications, say in differential equations when you're trying to find the inverse Laplace transform of certain functions, namely sines and cosines. But for now, I would just want to focus on this thing and see where we can get this and where it comes from. So here I've drawn a picture of what probably would be a standard monic quadratic polynomial. And you'll notice here that I have 4 shapes where I have a big square, 2 congruent rectangles, and a small square that I have a question mark in. And the idea is I want to complete the square by filling in this missing piece here. And that is done by thinking about the following. This square has area x squared. It has side lengths x by x. And then the 2 rectangles here, if you notice, if I do b over 2 plus b over 2, well, 1/2 b plus 1/2 b is a whole b. And so these rectangles have area b over 2 times x. Okay, they are b over 2y by x high. And the idea is I want to complete this picture in this space here. I want to figure out what to add to make that a bigger square. And that is where the name completing the square comes from. As we'll see, it's going to rely on the b over 2 part, the linear coefficient here. And so we'll go ahead and motivate this by example here by starting off by solving this equation here. X squared plus 6x minus 7 equals 0. Now, you can first probably try to factor this. You can go ahead, try to see if you can find 2 numbers that multiply to minus 7 and add to 6. But we'll go ahead and solve this by the method of completing the square. So the goal, again, I want to write this as x plus or possibly minus something squared equals a number, okay? I want to be able to write it in this form. Something squared equals something. Well, we need to figure out how to fill in the blank here. So if I think about expanding this, okay, remember that x plus, and I'll call our mystery number here alpha, okay? If I expand this using our product here, we'll have x squared plus 2 times alpha times x. Remember that it doesn't matter which order these are in, multiplication commutes in the real number system, plus alpha squared. And I want to be able to have this part equal to something that looks like this. Well, let's first look at our original equation here and notice that in the original, b is equal to 6. So b over 2 is 6 over 2, which is 3, okay? Now, if I look at my picture here, that means that the square, so I have my large square here, that is x squared, my rectangles that are 3x, And now I need to figure out what the missing piece is here. Well, the small side has length 3, this side has length 3, which form the sides of this square. And the area of the square is 3 times 3, which is 9. So I need to take this number and square it and add it to both sides of this equation. So I'll do that. We'll have x squared plus 6x, and perhaps I'll emphasize this in different color. I'm going to add 9 to both sides. It doesn't seem to work. And remember, we still have the -7 floating here. And in order to keep this the same, I'm going to add 9 to both sides. So I now have x squared plus 6x plus 9 minus 7 equals 9. Now, what I'll do is I'll add 7 to both sides, and I'll get x squared plus 6x plus 9 equals 9 plus 7, that's 16. And now this left-hand side, I can actually factor, because it's a perfect square, in something of this form. It is actually x plus 3 squared equals 16. And now I have this in the form something squared equals something. So now I can take square roots on both sides, not to forget the plus minus. So I'll have x plus 3 equals plus minus 4. And now if I subtract 3 from both sides, I get x equals minus 3 plus minus 4, which means my roots are minus 3 plus 4, that's 1, and minus 3 minus 4 minus 7. So that's how the technique of completing the square works. We need to figure out how to fill in the blank here to make this picture a bigger square, and accordingly factor so we can use square roots. So let's now actually go on to the next example here. I want to solve y squared plus 4y plus 1 equals 0. And so I need to write this as y plus something squared equals something. So the goal is to fill in the blanks here. So now let's try to mimic what we did here. If I think about this picture here, now instead I have, say, y by y, in this case here was x by x. I have a y by y square, that's the y squared. Then I have 2 rectangles that will add together to 4y, but I want to split them evenly. So that's 2y for each rectangle. And then I have this one left over that we're not going to worry about. Well, if I think about this, I can do y squared plus 4y plus something. That should equal y plus something. That is the goal there. Well, if I do the same thing here, I'll look at the linear term, that's 4. Take half of that, which is 2, and square it. And it turns out that it's 4. So now we can fill in our blanks here. So we'll add 4 to both sides of this equation here. Y squared plus 4y, and again, in red, I'll mark it, plus 4. And then we have our extra plus 1 here. And we'll add 4 on this side as well. So now I have y squared plus 4y plus 4 plus 1 equals 4. I'll subtract 1 and factor this part here. So this part's going to factor as y plus 2 squared. You can check that it gives these terms here. And then this is equal to 3, 4 minus 1. And now we solve using square roots as usual. We'll take the square root of both sides. Y plus 2 equals plus minus the square root of 3. And now I will subtract 2 from both sides. And so my solutions to this equation are y equals minus 2 plus minus square root of 3. And so what is the general strategy? The general strategy here, to complete the square, look at your linear term, your b, take half of it, square it, and then add it to both sides. And hopefully that's seen here in the picture. We'll need to take half the linear terms here to get two congruent rectangles. And then I need to multiply those two together, effectively squaring it because that's the shape here to get the area. And I need to add that so that I now have a perfect square. So I'll go ahead and clean up the board, and then we'll do two harder examples, this time with non-monic polynomials. All right, so now we have two slightly harder examples here. And you'll notice that in both of them, the leading coefficient, that is the coefficient on the squared terms, is now not 1. And so this makes them not monic. A monic polynomial, if you recall from the polynomial lecture, is one where the leading coefficient is 1. So this actually makes the process a tiny bit harder, but we just have to add one extra step. So for this first one, 5w squared minus 4w minus 2 equals 0, I want to use completing the square again. Now, again, you can try to factor, find two numbers that multiply to minus 10 and add to minus 4, or do some other magic. But let's try to complete the square. So when the leading coefficient is now not 1, so in the general quadratic case, so when a is not 1, and in fact, I'll generalize this to say when the absolute value of a is not 1, meaning if a is not plus or minus 1, okay, you need to transform your equation into a monic polynomial by dividing by a. So in this case, what I'll have to do is I'll need to divide both sides by 5. So let's actually see that in action here. I have 5w squared minus 4w minus 2 equals 0. And now I want to divide both sides by 5. Remember that on the left-hand side here, that just means dividing each coefficient by 5. Remember that 0 divided by a non-zero number is 0, so that stuff doesn't change. So here I'll have w squared, 5 divided by 5 is 1, minus 4 over 5w minus 2 over 5 equals 0. And now we just need to complete the square on this one. So again, let's use our general strategy, referring to our picture here. Let's take half, let's identify our linear term here. So b is now minus 4 over 5. And I want to take half of that. So when I divide by 2, okay, minus 4 over 5 divided by 2 should give me minus 2 over 5. And when I square it, effectively completing the square, this is 4 over 25. Remember that when you square any real number, it becomes positive no matter what. So let's go ahead and complete the square on this one. And I'll do the same thing I did on the last set of boards. So we'll have w squared minus 4 over 5. And then I'll put in a plus here for this term here. We're going to add 4 over 25 to both sides. Remember that this is 4 over 5w. Then I have the minus 2 over 5 left over here. And I'm going to add 4 over 25 to both sides. Now we clean up, add 2 over 5 to both sides, and we factor this. You'll see that this will actually factor as w minus 2 over 5, that's this thing right here, squared equals 4 over 25 plus 2 over 5. If you do that, that becomes 14 over 25. Okay, get a common denominator, you can check that. And now we take square roots on both sides. So this becomes w minus 2 over 5 equals plus minus the square root of 14 over square root of 25, the square root of Bayes-Ecke property, that it's multiplicative. But the square root of 25 is 5, so we'll just have 5 in the denominator there. And now when I add 2 over 5 to both sides, what I'll get is that w is equal to, and I can combine these because they have the same denominator. This is 2 plus minus the square root of 14 over 5. This is going to be the same thing we would get with the quadratic formula. And notice here that the square root of 14 cannot be simplified because it is square free. For this last example, we have 6u squared plus 69u minus 36 equals 0. Again, this is not modic, so we're going to have to transform it. We'll do that by dividing both sides by 6. When you do that, I'm going to skip writing it explicitly like I did here. When you do the transformation, should be u squared plus 23 over 2u minus 6 equals 0. Now we go ahead and do the process of completing the square, just like we had here, our previous two examples, and using this picture as reference. Well, we notice that b, the linear term, is 23 over 2. If we take half of that, that's going to be 23 over 4, and squaring. If I square 23 over 4, I end up getting 529. Yes, 529 over 16, and that's what we're going to add to both sides of this equation. So I'll do the same process that I did here on the other side. We have u squared plus 23 over 2u. Now I'm going to add this plus 529 over 16 with the leftover minus 6 equals, now I'm going to add this 529 over 16. And now when I clean this up and factor first these three terms, these actually come out to be u plus 23 over 4 squared. That's the b over 2 bit here. And then when I add 6 to both sides, okay, 6 times 16, I want to write 6 as something over 16. That's what we add and subtract fractions. 6 times 16 is going to be 60 plus 36, that's 96. And so this actually comes out to be 625 over 16. Now we can take square roots. So I have u plus 23 over 4 is equal to, well, 625 and 16 are actually perfect squares. This is going to be plus minus 25 over 4. And now when I move things over, I have minus 23 plus minus 25 over 4. And if I do the two solutions, do the plus minus here, I'll have minus 23 plus 25, that's a plus 2 over 4, so that's 1/2. And then minus 23 minus 25 is minus 48, divided by 4 is minus 12. And those are our two solutions of this quadratic equation. We can certainly check this by factoring. The corresponding factors here will be 2u minus 1 and u plus 12. You can certainly check that. But completing the square gives us a nice way of solving this equation without having to worry about factoring. Instead, we just have to worry about square roots.